Somewhere beyond the orbit of Pluto, there is a region of space where the temperature spikes to roughly 50,000 degrees Fahrenheit, hot enough to vaporize almost anything we know how to build. And one of humanity's oldest still functioning spacecraft flew straight through the middle of it. It didn't melt, it didn't even flinch. And the explanation for why not is one of the strangest, most counterintuitive facts in all of physics. Stick around, because I'm going to walk you through exactly what NASA's Voyager spacecraft found at the true edge of our solar system, why almost nobody on the mission team saw it coming, and why scientists are still working through what it means. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edge of our solar neighborhood. To understand why this discovery caught so many researchers off guard, you first need to understand what the Voyager missions were actually built to do, because heat measurements at the edge of interstellar space were never part of the original plan. Voyager 1 and Voyager 2 launched within about 2 weeks of each other in the late summer of 1977, designed primarily to take advantage of a rare planetary alignment that let both spacecraft use the gravity of Jupiter and Saturn to slingshot outward without needing to carry decades of extra fuel. Voyager 2 went on to become the only spacecraft in history to fly past Uranus and Neptune up close, a feat nothing else has repeated since. Once both spacecraft finished their planetary tours, NASA kept extending the mission again and again, sending the two probes deeper into the solar system's outer reaches, long after anyone expected them to still be functioning. Nobody involved in the original 1970s mission design seriously planned for these spacecraft to still be transmitting data decades later, let alone from a region of space nobody had ever directly sampled before. That region is called the Heliosphere, an enormous bubble carved out by the sun itself. The sun constantly releases a stream of charged particles known as the solar wind, and that outward pressure pushes back against the thin gas and plasma filling the space between stars, creating a kind of protective shell around our entire solar system that extends far past the orbit of every planet, roughly 3 times the distance to Pluto before it finally runs out of push. The boundary where that pressure finally gives way to true interstellar space is called the Heliopause. Voyager 1 crossed it first in August of 2012, becoming the first human-made object in history to leave the heliosphere entirely. Voyager 2 followed roughly 6 years later, crossing its own version of that same boundary in November of 2018 at a completely different location in the sky, giving scientists a second independent opportunity to study the same transition. It's worth appreciating just how limited scientists' understanding of this boundary was before either spacecraft actually got there. Ground-based telescopes and Earth-orbiting observatories can study the interstellar medium from a distance, measuring starlight passing through it or detecting faint traces of radiation, but none of that indirect observation can tell researchers what the density, temperature, and magnetic field actually feel like from the inside. Every model built before 2012 was, in a very real sense, an educated guess extrapolated from data collected safely within the protective bubble of our own heliosphere. Voyager 1 and Voyager 2 remain, to this day, the only 2 spacecraft that have ever directly sampled this region in situ, meaning their instruments are physically embedded in the environment they're measuring rather than observing it from a distance. That distinction matters enormously in a region where, as it turned out, conditions vary sharply from one patch of space to the next in ways no remote observation could have captured. Here's where the surprise comes in. Before either spacecraft actually reached that boundary, most researchers expected the transition between the solar wind and interstellar space to be relatively smooth and gradual, a slow fade from one environment into the next, cooling steadily as the sun's influence tapered off. Instead, both spacecraft recorded something closer to an abrupt threshold, a region where conditions shifted rapidly, rather than gently, almost like stepping over a line rather than drifting across a soft gradient. And the most startling part of that abrupt shift involved temperature. As each spacecraft approached the heliopause, instruments recorded the surrounding plasma spiking to somewhere between 30,000 and 50,000 Kelvin, which converts to roughly 54,000 to 90,000 degrees Fahrenheit. For context, that's hotter than the surface of many stars, and dramatically hotter than anything researchers had modeled for that region before either spacecraft actually got there to check. Naturally, this raised an obvious and slightly alarming question. If a region of space is genuinely that hot, why didn't it destroy the spacecraft passing through it? The answer comes down to a distinction that trips up a lot of people the first time they hear it explained, the difference between temperature and heat. Temperature describes how fast individual particles are moving. Heat describes how much total thermal energy is actually being transferred into an object. Those two things sound like they should always move together, and in the everyday world we live in, they usually do. But the plasma at the edge of the heliosphere is so extraordinarily thin, so sparsely populated with particles per cubic inch of space, that even though each individual particle is moving at extreme velocity, there simply aren't enough of them colliding with the spacecraft to transfer any meaningful amount of thermal energy. You could think of it a little like the difference between briefly touching a single spark from a sparkler versus holding your hand directly in a bonfire. The spark might technically be thousands of degrees, but there's so little material actually making contact with your skin that it barely registers. Out at the Heliopause, Voyager wasn't sitting inside a wall of fire in any conventional sense. It was passing through a region where a relatively small number of extremely fast-moving particles happened to register an extremely high temperature reading, without ever depositing enough actual energy to pose any real danger to the spacecraft's structure. To put the actual density involved into perspective, the plasma in this region contains only a tiny handful of particles per cubic inch of space, compared to the roughly 10 quintillion or so molecules packed into the same volume of air you're breathing right now. Even a temperature reading in the tens of thousands of degrees, spread across a population of particles that sparse, translates into an almost negligible amount of usable thermal energy. A spacecraft could sit inside a region like that indefinitely without ever registering so much as a noticeable rise in its own internal temperature, because there simply isn't enough physical material present to conduct that heat into anything solid. It's one of those cases where a single number, taken completely out of context, paints an entirely misleading picture of what's actually happening physically. The temperature reading is real and accurately measured. The danger implied by that number, if you're picturing it the way you'd picture standing next to an actual fire here on Earth, simply isn't. If you're finding this as strange as I did while researching it, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. That explanation didn't come easily, though, and it wasn't the only surprise buried in this discovery. When Voyager 1 first approached this boundary region back in 2012, its plasma temperature instrument had already stopped working, a casualty of decades of wear that had knocked it offline more than 3 decades earlier, back in 1980. That left scientists with magnetic field data and particle counts from Voyager 1, but no direct temperature reading from the spacecraft that actually made the historic crossing first. It wasn't until Voyager 2 approached its own version of the same boundary in 2018, with its plasma instrument still fully functional, that researchers finally got a direct, reliable temperature measurement of this region for the first time. That data, published across a set of 5 studies in the journal Nature Astronomy in 2019, confirmed what indirect measurements had hinted at, but couldn't fully prove on their own, that the plasma just outside the heliopause really was scorching hot by any conventional measure, hotter than researchers had predicted going in. But even that wasn't the end of the surprises, because Voyager 2 also detected something odd sitting just outside that boundary that didn't match expectations either, a patch of plasma that, while still hotter than the solar wind inside the heliosphere, came in roughly 10 times cooler than theoretical models had predicted for that specific location. That unexpected chill sent mission scientists scrambling for an explanation almost as urgently as the extreme heat had. John Richardson, the principal investigator for the plasma instrument aboard Voyager 2 at MIT, described it at the time as behaving like a genuinely new kind of shockwave, unlike anything researchers had previously cataloged anywhere else in the solar system. The leading explanation researchers eventually settled on was that a significant portion of the energy in that region was being funneled into a population of particles, moving fast enough that Voyager's plasma instrument simply couldn't detect them directly, effectively hiding a chunk of the total energy budget from the instrument's field of view and making the measured temperature look artificially cooler than the true total energy in that patch of space actually was. So within the same general boundary region, researchers ended up documenting both an unexpectedly scorching hot zone and an unexpectedly cool pocket sitting nearby, evidence that the true edge of our solar system isn't a single, uniform shell at all, but something closer to a patchwork of wildly different local conditions, shaped by turbulence, and particle physics that models built from the safety of Earth's orbit had consistently underestimated. Researchers have since taken to nicknaming the hotter regions the Wall of Fire, a phrase that captures the dramatic temperature readings, even though, as we've covered, there's no actual fire involved and nothing resembling a solid wall. There's a second layer of surprise tucked inside the same set of findings, and it involves the magnetic field rather than temperature. Before Voyager 1 crossed into interstellar space, many researchers expected the direction of the magnetic field to shift noticeably once the spacecraft left the heliosphere behind, since the field lines on either side of that boundary are shaped by completely different sources, the sun's own rotation on one side and the broader structure of the surrounding galaxy on the other. Instead, when Voyager 1 made the crossing, the magnetic field's direction barely changed at all, which left scientists with a single data point they couldn't fully interpret on its own. It could have been a genuine feature of the boundary, or it could have simply been a coincidence tied to Voyager 1's specific location and the specific conditions present in 2012. There was no way to know for certain with only one spacecraft's data to work from. That uncertainty held until Voyager 2 made its own crossing 6 years later, at a completely different point along the boundary. According to NASA's own account of the findings, Voyager 2's magnetometer confirmed the same surprising alignment that Voyager 1 had recorded years earlier, the magnetic field just outside the Heliopause, running essentially parallel to the magnetic field inside it. With 2 independent spacecraft crossing the boundary at different times and different locations, both recording the same unexpected alignment, researchers could finally rule out simple coincidence. Something about the way the interstellar magnetic field interacts with the outer edge of our heliosphere is apparently keeping the 2 fields far more aligned than anyone had modeled beforehand, and untangling exactly why remains an active area of research. It's worth pausing to explain why any of this actually matters beyond simple curiosity, because it's easy to treat extreme numbers like 50,000 Kelvin as nothing more than a dramatic headline. The boundary between our solar system and the rest of the galaxy determines how much cosmic radiation from other stars is able to reach the inner solar system, including Earth, and how much of the sun's own influence extends outward into interstellar space. A boundary defined by a smooth, gradual, predictable transition implies one kind of long-term space environment for anything traveling through it, including future spacecraft, and eventually, however far off, human missions attempting to leave the solar system entirely. A boundary defined instead by sudden temperature spikes, patchy hot and cold zones, and unexpectedly aligned magnetic fields implies something far more turbulent and far harder to predict, with real consequences for how engineers might eventually need to shield any future mission attempting to follow in Voyager's path. It also matters for a much older scientific debate over exactly how our sun and its heliosphere are shaped as they move through the surrounding galaxy. For decades, researchers modeled the heliosphere as something close to a simple, rounded bubble, gradually shrinking on the side, facing the direction of our sun's motion and stretching out somewhat like a windsock on the trailing side. The unexpectedly strong magnetic alignment and the sharp, patchy nature of the temperature boundary detected by both Voyager spacecraft have forced researchers to reconsider parts of that model, since the boundary, this turbulent and this variable from point to point, doesn't fit comfortably into the smooth, simplified shape that older models assumed. Some scientists now suspect the heliosphere's true shape may be considerably more complex and asymmetric than earlier diagrams suggested, though pinning down the exact geometry will likely require decades more data or an entirely new mission purpose, built to map the boundary in more detail than 2 aging planetary probes ever could. What makes all of this even more remarkable is the age and condition of the hardware actually collecting it. Voyager 1 and Voyager 2 are both approaching 50 years of continuous operation, running on radioisotope thermoelectric generators that convert the heat of decaying plutonium into electricity, a power source that loses a small amount of output every single year with absolutely no way to replace or recharge it. NASA engineers have had to shut down instrument after instrument over the decades simply to keep enough power flowing to whatever systems currently matter most, including the transmitters that let the spacecraft keep talking to Earth across a gap, so wide that a single radio signal takes over 22 hours to make the one-way trip from Voyager 1. Every one of these findings, the wall of fire, the unexpected cool pocket sitting beside it, the aligned magnetic fields, came from instruments built using technology from the 1970s, technology nobody involved in the original mission ever expected to still be gathering genuinely new science this far into the 21st century. There's also something worth appreciating about how these 2 specific discoveries reinforced each other. Voyager 1 crossed the boundary first, but did so with a broken temperature instrument, leaving researchers with an incomplete picture and a fair amount of uncertainty about whether what little data they did have was even representative of the boundary as a whole. It took Voyager 2, arriving 6 years later at an entirely different point along that same boundary, with its instruments still intact, to finally confirm that the earlier hints weren't a fluke. That pattern, an initial surprising result from one spacecraft, followed years later by independent confirmation from its twin, has repeated itself more than once across this mission's long history. And it's part of why NASA has continued extending funding for a project that, on paper, should have ended its useful life decades ago. It's a pattern that shows up again and again throughout this mission's history, going back even further than the Heliopause crossings themselves. Years before either spacecraft reached interstellar space, Voyager 1 and Voyager 2 crossed an earlier boundary called the termination shock, the point where the outward flowing solar wind abruptly slows down after slamming into the resistance of the surrounding interstellar medium. Researchers at the time expected that slowdown to be gradual, with the solar wind gently decelerating to a few 100,000 miles per hour. Instead, both spacecraft found the transition to be sudden and turbulent, accompanied by an unexpectedly strong magnetic field that was actively squashing and distorting the shape of the heliosphere's outer bubble, rather than the smooth, uniform sphere many models had predicted. Edward Stone, who served as Voyager's project scientist for decades, remarked at the time that these findings showed the interaction between our Sun and the surrounding interstellar environment was far more dynamic and complex than anyone had previously imagined. Nearly 2 decades later, the wall of fire discovery and the unexpected magnetic alignment findings have essentially proven him right all over again. NASA currently has no confirmed plans to send a dedicated new spacecraft back out to directly resample this boundary region. Any mission capable of reaching that same distance would require a minimum of 1 to 2 decades of travel time using current propulsion technology, and missions aimed at the outer solar system have historically struggled to compete for funding against projects promising faster scientific returns closer to home. There has been ongoing discussion within the scientific community about a dedicated interstellar probe mission designed from the ground up with modern instruments and a faster trajectory than either Voyager achieved. But that concept remains in the proposal stage, without a confirmed launch date or guaranteed funding. Until something like that actually happens, Voyager 1 and Voyager 2 remain the only 2 objects humanity has ever sent to directly sample this region, the only real on-site witnesses to whatever genuinely strange conditions exist out at the true edge of our solar system. So what does all of this actually add up to? A pair of nearly 50-year-old spacecraft, built with technology that predates the modern calculator, flew directly through a region of space hot enough to vaporize almost anything we could build today, and came out the other side completely unharmed, not because the danger wasn't real in some technical sense, but because the universe turned out to be far stranger and far more counterintuitive than a simple headline number could ever capture. Along the way, those same spacecraft found a magnetic field behaving in a way nobody predicted, a temperature boundary far patchier and more turbulent than any model anticipated, and evidence that the very shape of the bubble protecting our entire solar system might be more complicated than scientists assumed for decades. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Voyager is still out there, still transmitting, and there's a real chance the next signal it sends back adds another genuinely shocking piece to this puzzle. Thanks for watching, and I'll see you in the next one.